Okay, so this is Engineering Science 2143. We are reviewing for exam number 2. This is problem 4 from the fall of 2012 practice exam you all have in your module. And again, you should try setting this up on your own, working through, watching the video, maybe watching the video to a certain point and then seeing if you can finish it on your own. However you want to do it, okay? So we have a 2.75 kip load. It's applied to the end of rod AB. CBD is a rigid bar. AB and CE are A36 steel rods with cross-sectional area. DF is an aluminum rod with cross-sectional area connecting the rigid bar to a plastic shear block at F. Determine the vertical displacement at A. So that's way down here. So I can see that as I apply this load, I'm going to get some stretch, some deformation in AB. So part of my displacement at A is just from the deformation here. When we look at statics, if we pull down here at B, then we are going to cause forces to be in this cable and this cable. So this rigid bar could come down, it could rotate. We'll have to figure out if it comes straight down or rotates. As we apply a force here and we get this force in cable DF, we're going to cause our shear block to skew. And when it begins to skew, it's going to have that shear strain, which is going to result in a delta as this point here comes down because of the shear force that's acting on the block. So let's just start with organizing our data. I think that's the easiest way to get going here. So I have a length original of CE, and I know that this is A36 steel, so I have a yield stress of 36 KSI, and my modulus is 29,000 KSI, and I got these off of the equation sheet. We've already done that video. It has a cross-sectional area of 0.05 inches squared. When we look down here, we also have an original length of 20 inches. It's the same area of 0.05 inches squared. My modulus of elasticity is 29,000 KSI, and my yield stress is 36 KSI. I have to make sure that I'm within that 36 KSI for elastic behavior. Okay, over here, for cable DF, I have an original length. It is made of aluminum. I can go back to my cover sheet with all of my material properties, and this is going to be 60 KSI. My modulus is 10,600 KSI. It has a cross-sectional area of 0.2 inches squared, okay? And then I come up to my shear block, and again, I'm going to go to my cover sheet, which has all of my properties. For my shear block, my modulus of shear rigidity is 6 KSI. My yield stress, because again, I've got to make sure I'm staying within the elastic portion, so we'll have to check that, is 0.8 KSI. Okay, 0.8 KSI. And when I look at this, I'm going to note that this is 6 inches long. Its cross section is a 5 by 3 rectangle. So that's going to be the actual area that our shear force that's coming from this cable is acting over. So I think I have everything fairly well organized. So now let's start with equilibrium, because we always are going to start with equilibrium. And we have a free body diagram. So starting where my force is, I can note that I am applying a 2.75 kip force, and that means that my cable AB is going to have an equal and opposite amount of force. I can sum forces in the y direction and easily find that the force in AB is 2.75 kips. So I'm just going to go ahead and put that over here. Force of AB is 2.75 kips. Okay. Now, force of AB is going to come up, and if I cut my cable, okay, I know it's in tension, so I can draw pulling down in 2.75 kips. And I now have the force of CE and the force of DF, 15 inches, 12 inches, and I can sum the moments about point C. So I'll have 2.75 times 12, okay, equals 15 times force DF, and quickly discover that force DF equals 1.222 kips. I can now sum forces in the y direction, and I can get that force in CE equals 1.527. Oh, you guys can't see that. Sorry, 1.527 kips. So I'm just going to go back up here and write. Here we have the force in CE is 1.527 kips. Over here we have the force in DF is 1.222 kips. And then I can note, we're going to erase that, that's where I cut it, that I have this shear block, okay, and it's going to have a shear force that's acting on it, and that shear force, okay, we can look at it, we can sum forces in the y direction, that shear force has to equal the force in cable DF. So we can go back up here with our shear block, and I can write then that my shear on the shear block is 1.222 kips, okay? So I now have these internal forces, and if I know the force, and I know the modulus of elasticity, and I know my areas, then I can actually go back and I can calculate delta, because delta equals PL over AE. And where did I get that? Where did I get that? Stress equals E times strain, and I know we're dealing with normal stress because we're in tension. And if I'm dealing with normal stress, then I am looking at that internal normal force divided by cross-sectional area equals E. Strain is change in length over original length. So if I'm trying to find that deformation, I have areas, I have internal force, I have modulus of elasticity, I have original length, and I can now get my deltas, okay? So let's look at deformation. Let's look at our free body diagram of deformation. So the first thing is I have this cable. I want to find eventually how far down A goes. So I have this cable from B to A. And as I load it, it is going to have some elongation, delta AB. Okay, so that's a little bit of where A to A prime goes. Okay, now I also have this rigid bar, and those cables above it are going to stretch, and I don't know how much, if it turns, if it twists, if it stays level as it comes down, I don't know, but I am going to go from C to C prime. Note that I have B to B prime and D to D prime, and I know that this has to just be the change in length from C to E. That's the only thing that's on this. This has to be the change in length from D to F plus that delta that I'm going to get from the shear block, because as we pull this down, this is going to, okay, it's going to have that rotation where we have gamma, and if we have a gamma, we have a delta that's coming down on our shear block, okay? So now when I look at my delta of A to A prime, it's going to be a combination of the elongation of cable AB plus, okay, plus the change from B to B prime, which comes from the cables and the shear block up above it, okay? So we have a lot of work to do. I'm going to start at the top and work my way down. So let's just start with cable CE. Okay, let's just start with cable CE. That's the easiest thing to start with because it is the only thing on that side. When I'm looking at cable CE, I can see that it is in normal stress because it's a tensile force. So I have stress equals E times strain. And stress is that internal normal divided by cross-sectional area, E. And then I have delta over original length. So I have everything I need so I can calculate delta CE. But the first thing I need to do is I need to check, are we in the elastic region? Are we elastic? And how do I do that? I know that my yield stress is 36 KSI, so I have to be less than yield stress. And the stress that I have in cable CE is equal to that normal force of 1.527 kips divided by that cross-sectional area, 0.05 inches squared. And when I multiply this out, or divide this out rather, I'm sorry, I get 30.56 KSI, which is indeed less than 36 KSI. So this is a valid solution. Okay, so we have our stress of 30.56 KSI equals 29,000 KSI, that's my modulus of elasticity, times delta C to E over that original length. And again, it's nice to have all of my information organized because I don't have to go back and hunting and reading. So when I do this, I can take my 30.56, multiply by 30, divide by 29,000, and I am left with delta from C to E equals 0.0311609. Up there it says out to 4 digits. 1, 2, so I want to at least keep 4 digits here, if not more, so that I don't have rounding issues. So we have a displacement then at point C. We have an elongation of our cable of 0.03. So that's what goes in this box right here. Now I need to work on the d to d prime. So I've got a blank piece of paper and we're going to put it up here so we can see everything. Okay, we can see everything. So now let's look at cable DF. Okay, and again, I note that it is in tension, so we're in normal loading, so we have stress equals E times strain, which is that internal normal force over area, E times delta of DF over the original length of DF. But is it elastic? Is it elastic? How do I check? The yield stress is 60 KSI. So I need to make sure that that is greater than the actual stress I'm experiencing, which is that's my internal normal, 1.222 kips divided by cross-sectional area, 0.2 inches squared. When I multiply, or sorry, not multiply, when I divide this out, I get 6.1 KSI, which is definitely less than 60 KSI. So I am indeed elastic. So I can go back and use this equation. So I'm going to just go ahead and rewrite that delta DF equals N times length divided by A times E. So I have 1.222 kips times the original length of 20 inches divided by 0.2 inches squared and E of 10,600 KSI. So pretty easy peasy. And when I divide this out, so let's look at this. When I divide this out, then I get 0.01150.9 inches. 1, 2, 3, 4. I'm at least 4, and I'm going to take 2 more for good measure. Okay, so 0.011509. So this is my delta of D to F. So that is one part of my problem that I'm coming over here for my deformation. And guys, please note how this is somewhat organized in terms of presentation, and you can easily see what I'm doing. It just makes it more helpful if you have a plan, and it makes it easier for us to grade and make sure you get the partial credit you deserve. Okay, shear block. So when I look at a shear block, okay, here's my block, it's attached. I know that this is 6 inches. I know that I'm going to be applying that shear force of 1.222 kips, and it's going to be applied across that front cross section, which is 3 to 5. And when we do that, we're going to get gamma. Okay, So I have the shear force, I have some area, I know G. How do I find gamma? Well, again, shear stress equals the shear modulus times shear strain, okay? Shear stress equals shear modulus times shear strain, where our shear stress is just that force over cross-sectional area, G, and then we have shear strain. So the first thing we have to do is this elastic behavior? Are we in the elastic region? Well, how do I check? My yield stress for shear was 0.8 KSI. That was given as my material property. The shear stress that I'm experiencing is 1.222 kips divided by 15 inches squared. 5 times 3 is 15 inches squared. When I multiply this out, I get a shear stress, okay? I get a shear stress of, let me find my calculator because I don't have this number written down. 1.222 divided by 15 equals, and I get a shear stress of 0.08 KSI, which is much less than the yield. So I am an elastic. I am in the elastic region. Okay, it is elastic behavior. So now we can go back. We have 0.8 KSI equals G. The G was given as 6 KSI gamma. So my shear strain is 0.8. Well, actually, it's more than that. I just rounded. Okay, it's a really big number. Well, a really tiny number, but divided by 6 equals, and I get a gamma of 0.013577778. And remember, this is in units of radians. Okay, you have to remember this is in units of radians. And so now what can I do with this? Okay, what can I do with this? Well, that's how much of that deformation I get, that skewing. It's like cutting bread. Remember, it's going to be that skew, that angle that I get. So if I know this number, which is very, very small, so this is a small strain, then I can go back and look at, well, if I think about trig, tangent theta equals opposite over adjacent, okay? Where opposite is my delta, the amount that this position moves down. Because it's small strains, I don't have to use tangent, and I can just use my gamma as is. So gamma equals, so it'd be like tan theta equals opposite over adjacent. And so I can now rewrite this, that delta, because of my shear, equals, that's because of my shear, equals gamma, that rotation I found, times 6 inches. And so I have this value in radians times 6 equals, and I get 0.081466667 inches. Okay, I get that value right here, and this is my delta because of shear. So if I want then the entire displacement from D to D prime, it is that delta from D to F plus the delta from shear. Okay, it is just those two things added up. So I've got this number in my calculator. I'm going to go back and add that plus 0.011509 equals, and I get that the delta from D to D prime is 0.09297567 inches. Okay, so there I have that. So what am I going to do with this number? Okay, this goes back to our deformation. Because I know the whole bar is coming down and possibly rotating. So let's go back and draw this picture. Okay, and we're going to draw it pretty big just so we can see it. And I'm going to note that these numbers, it does rotate. Not only does it come down, but it rotates. So here I have 0.0929757 inches. And over on this side, that was my delta CE. That was 0.03. 1609, 1609. So this went from C to C prime, this went from D to D prime, and here I have B to B prime. This is 15 inches and this is 12 inches, okay? So because of rigid body rotation, which is super, super nice, okay, I know that I don't have any discontinuity in the shape from C prime to D prime. It just, the whole thing rotates. And I can kind of pull out like this little bitty, like similar triangles. So I know that this is 0.031609 and this value is the same thing. So I can actually go back and calculate this, okay? This piece of the puzzle. So if the whole from D to D prime is 0.0929, then this little piece is 0.09297567 inches minus, okay, minus what C to C prime went down, 0.031609, and I get a value there. When I rotate that down, I get a value that this point down is actually 6 point, well, that's really very quite large. Okay, 0.0613669. Okay, and now I can use the similar triangles to calculate this little smidgen right here. So I know that this part is 0.03 because that's how much we went down. So let's just cut that off. We've already taken that into account. Let's find this little smidgen. Okay, 0.0613669 is to, okay, all the way back is 15 plus 12, 27 inches, as this little smidgen, okay, is to 12 inches, okay, is to 12 inches. So I can then calculate, okay, I can calculate what that little tiny smidgen is. And I know that when I go from the delta from B to B prime, it's going to be 0.031609 plus this little smidgen of my similar triangle. So let's get that value. Okay, minus 0.031609 equals, okay, so times 12 divided by 27 equals, and I get that this delta is 0.2727407. Okay, so now let's find our total delta B to B prime. Plus 0.0311609 equals, and I get 0.0588837 inches down. Okay, which is perfect. Now I have a big piece of my puzzle. If I go back and look, I know that when I want to find the whole displacement of A to the final after I measure, I have to deal with everything above the bar. Check. Now I need to go back and look at delta AB. Okay, delta AB. So let's look at cable AB. Okay, with cable AB, again, it's in tension, so it's normal stress equals E times strain. And I need to make sure, are we in the elastic region? Are we in the elastic? I don't know. How can I check? Well, my yield is 36 KSI. So I need to make sure that what I'm actually experiencing is less than that. So we have an internal force of 2.75 kips divided by a cross-sectional area of 0.05 inches squared. And when I do that, I'm going to get 55 KSI, which is much larger than 36 KSI. Is it elastic? No, it's not. Can I use this? No, I can't. What do I have to do? I have to go back and find my stress strain curve for my steel, which I had printed out. Here we go. I have to go back and find my stress strain curve, which is given in your exam. Okay, it's given in your exam. I'm trying to figure out how to not be zoomed in so much, but this is about as good as I can get. And so it's at 55 KSI. So I have to go back then, and 55 KSI is between 50 and 60. And when I'm looking at this again, remember these bottom ones are for the elastic region. These top ones are for the not elastic region. So let's find my straight edge, and we're going to guesstimate this as best we can. Okay, so if I come across here like so, this comes roughly over like this. That looks fairly straight. And then we're going to come down, and I'm going to, again, I have to come down as straight as I possibly can. That's a straight line, so we're going to go right there. We're going to come down like so. And if this is 0.1 and this is 0.2, this has to be 0.15. And I would say I'm maybe not quite at 0.11, but we could call that 0.105. So I'm just going to call that strain 0.105. So now that I did that, I get a strain of 0.105 inch per inch. Okay. What is strain? Strain is change in length over original length. So I have 0.105 inch per inch, that's my strain, equals the actual change in length of cable AB, and my original length was 20 inches. When I do this, delta AB equals, okay, 0.105 times 20. So I have 2.1 inches. I'm going to tell you that is much bigger than what I would have gotten had I just used stress equals E times strain. So now we've got all the pieces of our puzzle. So the change in position from A to A prime equals 2.1 inches plus that delta B to B prime, which we found was 0. Here it is, right here. 0.0588307 inches. It also displaced down. So A to A prime equals, let's go back and add all of this up, plus 0.058888307 equals, I get a displacement of 2.1, not 21, 2.1589 inches down equals delta A prime. And there you have it.